much. Let me just share my screen here.
Yeah.
So I think you can see it, and you can see my mouse, I hope.
Yeah, we can see.
And you can clearly hear me. That's good.
Yeah.
All right.
Yeah.
So thank you for coming back. It's always a risk after the first lecture whether or not people will come back for the second one. But I appreciate those who have done so, having done so. So I'm going to pick it up essentially where I left off last time. So just to remind you where that was. I forget why I didn't delete this slide. I was going to skip that slide. So these are the topics that we've been talking about in the first half, the general framework. I got most of the way through. That was these topics. I've covered the first three, and so I was going to pick up today where I left off, where the focus will be on effective field theory, the story in the case where the classical background, if we're doing a semi-classical expansion, in the case where the classical background is not the vacuum, so it's some other time-dependent solution. It's a kind of a situation that we often ignore in particle physics, but it's one which applies, it's very pertinent to cosmology and other areas in physics, and so it's worth talking about the new issues that arise. And the short version of it is that the methods of effective field theory apply. There's a domain of validity for them, and in a time-dependent situation, there's a few additional new conditions you have to satisfy, but it's apart from that very much as it was. And then I will then continue on to the examples part, where really the thing about examples in effective field theories is that all of science is an example, and I'm here cherry picking a couple of illustrative things which hopefully will be useful for later lecturers and also are interesting in their own right. And I'm choosing of these examples the ones which are more tailored to a particle physics audience, but there are as many or more examples that you could have also done in other areas of physics like condensed matter physics and elsewhere. Okay, so let's get back to the time-dependent fields. And again, I'd like to talk about this issue of time dependence, how you deal with situations where there's a time-dependent background field in the context of this toy model that we were talking about with a complex scalar field with a Mexican hat potential so that the scalar field has a non-zero value in the vacuum. Field was massless, as it turned out. It was a Goldstone boson. And so this is the framework I'd like to ask specifically about time-dependent fields again. And before I launch into this, I just remind you, if you have questions, just jump right in and interrupt me, or put them in the chat. And hopefully, if I miss them in the chat, which could happen, although I have the chat window open, someone can draw my attention to that by interrupting me if I miss it. Okay, so let's, what's the big deal about time-dependent background fields? The reason I'm talking about it is that you might have worried that the way I've phrased the effective field theory formalism, it sounds like it kind of can't be describing used in a situation where things are time-dependent, because the way I phrased it, it was all about, we're looking at a subset of the system, but the subset that we're looking at was chosen with energy as a criterion, and it was important that energy be conserved for that, in the sense that we start off in some low energy sector, and then we evolve forward in time, and we were guaranteed that we were going to end up with the same degrees of freedom that we started off with because of the conservation law. Conservation of energy was going to forbid us producing these particles that we were choosing to ignore. So the worry would be that if you have a time-dependent background, although energy might be conserved, including the time-dependent, the energy in the background, the energy of the fluctuations around the background needn't be conserved, because it can, the fluctuations can exchange energy with the background. And so you might ask then, so does that ability to exchange energy cause a problem for setting up the formalism? And it can. So if you have a rapidly oscillating background, which can liberate energy by just directly pair producing particles that are high energy, that would be a problem, because that would be the kind of thing that would give you final particles that are in this high energy sector that you assumed were not there initially. And so there will be a constraint on how rapidly the background can depend on time. And that has to also be a low energy scale in order for the picture to work. But modulo that kind of a constraint, it'll all work out. So the key idea is that you want the background to be adiabatic, that the assertion that this effective theory that we're going to write down, including looking at its classical field equations and asking how it evolves background fields, the assertion that that captures the evolution of fields in the full theory, including the high energy degrees of freedom, will only be true for adiabatic motion. And so adiabatic motion, I'm thinking here, I'm using, you have any variable in your problem at all, typically it's some field, but A I'm just using as some generic thing. If I take 1 over A dA dt, that's a characteristic energy scale, which is sampling the time dependence of A, where the scales in A itself have dropped out. That's why I'm dividing by A. So that's a scale that's intrinsic to the time dependence. And what we're going to ask is that scale always be small compared to the ultraviolet scale, the heavy scale, and in the case of the toy model, the mass scale of the heavy particle. And the point of the adiabatic approximation is that it means that because the evolution of the background is slow compared to the timescales of interest in the physical processes that we're interested in, so we can think of the energy as being kind of parametrically a function of time. And so, and because it's slow, you don't get transitions between energy levels because there's not enough energy in the background, not enough energy, the frequency of the time evolution of the background is slow enough that you're never getting enough energy that you can promote yourself from a low energy state to a high energy state that you've integrated out. And so in that kind of a situation where the energy levels are just all kind of evolving along, if you start off in an approximate energy level, you'll stay in it, but the actual energy might evolve in time due to the adiabatic motion. That's the kind of situation where this whole effective field theory framework will go through as it did before, with one proviso. You have to make sure that you're always asking that the gap, there has a big gap between the energies of interest to you, your low energies, and the energies that you're trying to ignore, such as the mass of the heavy particle in this toy model. That gap has to stay large. And so you have to avoid situations where there could be situations where that gap gets smaller with time as the energy levels evolve, that the lower ones might come up or the higher ones might come down. And if that happens, so the bottom picture here is supposed to be a plot of energy levels against time, and the dashed line is supposed to be the dividing place between low energies and high energies. And we're assuming that there's a big hierarchy between the low energies and high energies. The main new thing you have to ask, in addition to being adiabatic, is that this evolution doesn't remove this hierarchy. So you don't want something like on the right here, where a high energy state comes down, a low energy state comes up. They never actually cross at the end of the day. You know that levels always repel. But what'll happen at this point is that it won't be adiabatic anymore. And so the assumptions that go into this, the way things work, will typically break down in that situation. So there's no guarantee that just because you started in a situation where an effective field theory works, that you'll stay there as time goes on. You have to check that, but given that you check that, then it's okay. So just to make that concrete, let's go back to our toy model. Here's the toy model, just to remind you. It's a complex scalar field with a potential, a Mexican hat potential, which is minimized at phi equals v. Previous to now, we've been expanding around phi equals v as the classical solution, and that's of course a time-independent solution. And then we've been looking at the scattering of particles around that background. But now let's do something different. So before I go to the different thing, I just remind you that we found that the low energy limit of scattering in this case was well described to leading order in 1 over m by this interaction. And I see that I've put a typo in here. This should be m to the 4th that's appearing here on dimensional grounds, because this has the interaction has dimensions mass to the 8th, and the action has to be dimensionless. So then the d4x gets rid of 4 powers of mass. So there should have been an m to the 4th here, not a m to the m squared. To apologize for that. So we found that scattering was well described by this interaction. I showed it for 2-to-2 scattering, but it could have I claimed that it's true, and you've seen what the arguments why it should be true. this describes all kinds of scattering. We could have looked at 4 to 8 scattering, and this will be controlling the low energy. The first corrections at low energies that depend on 1 over amp will come from this interaction. But now I'd like to ask, how does the system behave if we look at expanding around a classical background which is not time independent? So here's one. So if I take the configuration phi equals some constant rho naught times e to the I omega t, where omega is a parameter, and that's the speed with which that's a configuration where this complex field is moving in a circle of radius rho naught. If I stick that into the classical equations of motion, which are the ones that are coming from this action, the full action, what I find is that it tells me what the value of rho naught has to be, and it has to be given by this. It's bigger than v. If omega had been 0, so that if things were not rolling, then we would have lost this term, and we would have had rho naught equals v, and that's the solution we had before, where you're sitting at the minimum of the Mexican hat. But what's happening now is that rho naught is being required to be bigger than v, and you kind of physically have an intuition for why that's happening. Is that if you're kind of going around, if you were rolling around this circle here, what's happening is that there's a centrifugal force, so you kind of slide up the side of the hill until you reach the point where the centrifugal force is being balanced by the slope of the potential. And that's how that's why the equations of motion tell you what rho naught has to be. And how far you go depends on how fast you are rolling. And so, and that you can see that here is that the bigger omega is, the bigger rho naught is. So what's important about that is that the energy that motion has, it depends very much on the potential, because if I look at the energy of this motion, of this particular configuration, it's given by phi dot squared plus the potential. That's always the energy, given that that's the energy density, given that there's no gradients, spatial gradients. And so if I evaluate this at that solution, I get an expression like this. And the number 3 here is important, because the contributions that we're getting here, there's of course everything vanishes if omega goes to 0. That's the case where you're sitting at rest. But the total energy is coming in from 2 sources. One source is the kinetic energy. So there's no surprise that we're going to get something going like omega squared, because that'll be what the kinetic energy will want to do. But there's also a contribution coming from potential energy, because the motion is driving you up the side of the hill, and so because you've gone up the hill a little bit, you've got a little bit of potential energy. How much you've been driven up depends on omega, so that potential energy will be omega dependent. And the difference between I think 3 and 2, I think if we ignored the potential energy, we would not have a 3 here, we'd have a 2. So the size of this numerical coefficient in the second term here is the one that includes it's partly coming from potential energy. Now you might ask that I'd like to ask, how does that classical evolution picture look in the effective theory? If I choose the frequency to be small compared to the mass, which I have to do if the frequency is bigger than the mass, then the oscillations in this background can directly pair produce the heavy particle that I'm trying to ignore. And so I have to restrict omega to be much smaller than the mass. But in that regime, I can still look at this evolving background field, and I can ask in particular, what's its energy purely within the effective theory? And one question that seems paradoxical is how can I get the energy right, given that I don't have a potential? The low energy theory just involves the Goldstone boson, you remember, and kind of it was a success of that theory that it did not appear in the potential, because that was explaining why Goldstone bosons scatter less rapidly at low energies. Their scattering was suppressed by powers of energy because all their interactions were derivative interactions. And so that was being driven by the fact that they don't live in the potential. So now how can it possibly be that effective theory can capture this physics of the motion of the field that we're not following, the radial field, climbing the hill a little bit up the potential? So what you do if you just follow your nose, there's a solution to the effective theory. The equations of motion in the effective theory are just box C equals 0. One solution to that is something where C is linear in time, and that's clearly the analog of the rotating solution in the full theory, because C, the light field, is just the phase, remember, of the full field phi. So if I take that solution and I ask, what does the energy density look like? There's a contribution coming from the usual kinetic energy, the C dot squared term. But there's also a contribution coming from that new interaction, and the new interaction had 4 derivatives in it. It had 4 powers of fields and 4 derivatives, and so that'll become a C dot to the 4th term, and it turns out to have this coefficient. And if I evaluate this at the solution where C is linear in time, so C is going like omega t, I get this. And you see that the numerical factors are exactly what they needed to be in order to capture the total energy of the full theory, including the potential energy part of it in the full theory. And that all worked, but it only worked because when I calculated the energy, I used this specific interaction. This is the one that gave us the C dot to the fourth term with this specific coefficient. So at the very beginning of yesterday's lecture, I was arguing that this one operator captures the physics for all observables at low energies. The same operator captures the physics for all the observables. And here's an example of that now. And that I've so far really only showed you how scattering was working for one kind of scattering, but I've now shown you that this particular interaction with this particular coefficient in front of it is capturing the classical evolution of the scalar field as it rolls around the hill in precisely the right way. And this operator's role in that is to capture the part of the energy that's coming from, partly coming from the climbing of the microscopic field phi up the side of its potential, even though that potential is not there in the low energy theory. That shows up as a frequency dependence in the energy, a change in the frequency dependence at order omega to the fourth. Okay, so that's all I really want to say about time-dependent backgrounds. The reason this is important is that you're going to see that when we talk about gravity at the end, there's really no alternative to talking about gravity except as an effective field theory, because it turns out gravity is not a renormalizable theory. That is to say, the effective couplings that it has, like in this toy model, have dimensions of 1 over a mass to some power. Those kind of theories are ones you remember when we talked about the toy model, terms, the more complicated an interaction looked, the higher the dimension the fields and the derivatives had in the Lagrangian, the more powers of 1 over m had to be in the coefficients of the Lagrangian, the effective couplings. And so the more suppressed those terms were at low energies. And so that meant that the most important terms were the ones that were least suppressed. And in particular, the things that should dominate at low energies, I argued, were the renormalizable terms, the ones for which the couplings involve non-negative powers of mass and dimension. And so those are the ones that you would normally expect to be important at low energies. So non-renormalizable theories are ones where all the couplings are have negative powers of mass, and so those are the ones for which the power counting story that I gave last lecture that quantify how big the various effects are in deciding how big observables are. The size of contributions to observables was controlled by a power counting argument that I gave yesterday. And it organized predictions in powers of the energy of the process we were interested in, divided by the heavy scale, in this case m. And it told you precisely which interactions were important at any order in that expansion. But it also said that the expansion in energy divided by m was crucial for that whole perturbative description to work. And so that the lesson there, which I probably didn't emphasize strongly enough, was that whenever you have interactions that whose couplings have the dimensions of negative powers of mass, you're effectively always doing a low energy expansion, even if you didn't realize you were. And gravity is an example of that. Because Newton's constant has dimensions of inverse powers of mass, it will be an example where there's always an effective low energy expansion going on. And that's what controls, that's why the classical approximation, that expansion is what justifies using classical techniques in gravity, is what I'm going to argue later on. And so if you're interested in cosmology, and in particular, if you're interested in cosmology where quantum effects are important, as people are in, say, inflation, there's no alternative to this kind of a language, effective field theory language, to quantify your errors in making your predictions in that context. And if you could not have done the effective field theory techniques in a time-dependent background, it would have been fatal to the program. So these kind of arguments that I'm giving here apply equally well in the gravity case. And I won't say so much about the time dependence in that case, but the importance of these arguments is, in my mind, partly coming from that. So that's the end of the generalities. This might be a natural place to pause for questions if there are any, before looking into some examples. But if not, then I'll push forward. But please do interrupt if something hits you. So I'm going to go through the 4 categories of areas with some examples, partly to illustrate what's going on, to show you how it's similar to the toy model that we've been discussing, and also to point out how some of the things that came up work in more complicated examples, and also some things come up that didn't come up in the toy model that are interesting to track in their own right. So I'm going to start with the particle physics audience. So I'm going to start with the standard model, partly because it's got so many clear examples, and it has the virtue that the standard model I can think of, there's many ways to think of effective field theories in the context of the standard model. In one of them, the whole standard model is the low energy theory, and I could ask, does it look like it's the low energy limit of something more fundamental that I don't understand? That's one useful way to think about it, and that's what you're going to hear about a lot in the other lectures. I'm going to mostly be focusing on other examples where some of the scales in the standard model has many scales. It ranges from the top quark mass, which is just shy of 200 GeV, down to the electron mass and lighter for photons. There's many hierarchies of scales in the standard model, and effective field theories are actually very useful in exploiting the predictions of the standard model, getting to the predictions efficiently by exploiting those hierarchies of scale. And they have the advantage that you understand both the high energy and low energy end, so that you can be very concrete about how everything fits together. So I'll start with a couple examples like that, and then we branch out from that. Of course, the poster child for this whole thing is the weak interactions. We know that in the standard model, particle decays, for example, the muon decays are happening because the W boson is emitted and reabsorbed. The basic interaction in the standard model that does that is linear in the W boson and involves bilinears of the spin-half particles. These currents are the things that would be describing the pairs that are participating in the charge current weak interactions. W is complex, of course, because it's a charged boson, and so you have to add the complex conjugate to have a Hermitian Hamiltonian. And it's kind of well known that this graph is very much like the one in our toy model. If we're at energies very low compared to the mass of the W boson, then it should be true that we can kind of basically, we won't be able to resolve how far the W boson has gone, because the uncertainty principle will keep it from going very far, and this should degenerate into some local 4 Fermi interaction. And of course, that's historically what came first. Was the 4 Fermi interaction was proposed to describe the weak interactions, and it wasn't in its final form when Fermi proposed it, but it became souped up over the years. And it has, not surprisingly, the proposal that worked was, in retrospect, a product of this current twice, which is describing both ends of this graph. So that's this thing. And it's effectively obtained by doing what we did with the standard model and Taylor expanding the W boson propagator and stopping at leading order. And that picture allows us to compute this measurable Fermi constant in terms of things in the standard model, the coupling of W bosons to things, a universal dimensionless constant, little g, and the mass of the W boson in this particular way at lowest order in perturbation theory. And this is, of course, a very successful prediction. We can measure everything here. The way that this is normally treated now is that you measure G Fermi in some decay, because you can measure it very well. And you can measure G, which is related to the electromagnetic fine structure constant, and other things you can measure elsewhere. And you can use this, turn this into a prediction for the W mass, which works very well, including corrections to it. So this picture is very nice. It kind of gives a lot of intuition for if you have a coupling which has dimensions of inverse powers of mass, this could be what's going on. You're kind of getting a feeling for what the mass is. The particle that was being exchanged it could have been due to some renormalizable interaction. In the end of the day, the standard model, the weak interactions are very similar to the electromagnetic interactions, although they don't look like that at low energies, just because the photon is massless and the W boson is massive. And so the weak interactions in hindsight are not weak because they were intrinsically weak. The coupling G is not very small. They were only weak because we were looking at them historically at energies low compared to the W boson mass. And that's why, and that the clue for that was that our coupling was involving an inverse powers of mass. Now, it's not true that the coupling is directly telling you the mass. G Fermi here is, numerically, it's 1 over an energy squared, and that energy is 246 GeV. The mass of the W boson isn't 246 GeV, it's 80 GeV. And the difference is coming from these other factors. And in particular, the weaker the coupling gets, the smaller the mass gets, and that keeps this ratio fixed. And so that's a natural thing to come back to when we talk about gravity, because with gravity, Planck mass is defined as the Newton's constant is 1 over an energy scale squared. It's much higher energy in that case because the force is much weaker. And this suggests that there might be some ultraviolet picture for gravity in which there's more like or normalizable. It's a dimensionless coupling that will be controlling the exchange of something that's heavy. And it makes it look like the gravitational interactions we see at low energies in general relativity might be the low energy limit of something more fundamental. And that's kind of the direction that string theory has taken. It's the first candidate we have of a theory that could have been that microscopic theory that reproduces general relativity at low energies. All right, so that's kind of the poster child of low energy limits. But so let's go right down to super low energies in the standard model, and that should be the thing where we effective field theory should be the most useful. And here, in another one of Weinberg's insights, there is actually a very powerful statement that gets said about what's going on at the very lowest of energies in the standard model. That's where the massless particles are basically dominating, or massless or near massless. So once we get down to super low energies, the lowest energy particles in the standard model are the photon, the neutrinos. They may have a mass. The standard model predicts they have 0 mass, but if we generalize the standard model as the low energy limit of something, and so include non-normalizable or higher dimension interactions, then the neutrinos can have a mass. But those masses can't be super heavy, heavier than about an electron volt. And so they could be in your super low energy theory. Depending on how low energies you're talking about, the electron may have been integrated out or not, and you could ask what's going on at very low energies. If you're at super low energies below the electron mass, then all you'd have is, say, the neutrinos and the photon, which I'll come back to actually after this. I probably should have talked about that first because that's the natural lowest energy case. What I'm first going to talk about is what would we expect the low energy interactions of a photon and an electron to look like? And the point of the story will be really the most general thing you could have is what we do have, and that's just electromagnetism, it's QED. And that's because that low energies, massless particles at low energies have very special properties to do with gauge invariance, and those are being dictated. Often those are phrased as gauge invariance is phrased as an extra assumption for the theory, but one of the things you learn from effective field theories is that it's actually a consequence of quantum mechanics and special relativity. And so I kind of am alluding to a deeper argument here, again, largely due to Weinberg. So the starting point when we ask what a photon could do at low energies is to ask what's the field that we would represent it with. And that's a problem that was solved in generality, again, by Weinberg in the 60s. You give me a particle, a massless particle of a given spin, and I can tell you what classes of fields are allowed to represent it. And they're all equivalent to one another by differentiation. And so it's really, there's a complete list of, it's not like there's an ambiguity in what the fields are. It turns out that the simplest example, the simplest field that can represent a massless spin 1 particle is not a vector field, which is what you might have thought if you're experienced with quantum electrodynamics. It's an antisymmetric tensor field is the thing, that's the smallest dimension representation of the Lorentz group for a field that can represent a massless spin 1 particle. Now, it turns out that an arbitrary antisymmetric tensor can't do it. The requirement that you're representing a massless spin 1 particle implies that this F mu has to, if you expand it in terms of creation and annihilation operators, the coefficients have to depend on momentum in a way which amounts to saying that it's the curl of something. So it's d mu a nu minus d nu a mu. And so you might say, well, if making F mu represent a spin 1 particle that's massless implies that it's the curl of something, then I must have lied to you before by saying that it can't be represented by a vector field, a mu, because here's the vector field. I'll just take the thing that I took the curl of, and I'll write that in terms of creation and annihilation operators, and that has to be the vector field that will represent a massless spin 1 particle. And the reason I didn't lie to you is that there's a subtlety there. If you ask, how does that vector field that you're led to transform under Lorentz transformations, the thing that you're taking the curl of to get F mu is not a 4 vector. If I ask, I know how particles transform under Lorentz transformations. If I ask how they transform, and I've taken A and written it in terms of creation and annihilation operators as we standardly do, and I ask how does A transform under Lorentz transformation, the answer is it's not a 4 vector. It's the 4 vector up to gauge transformation. So it's a 4-vector up to a thing where I shift the vector by a gradient. And so what that means is that if I want to make a Lorentz invariant interactions between the spin 1 particle that are not suppressed at low energy, so they're not derivative interactions. So I can't build them out of F itself because that has derivatives in it. I have to build it out of A. If I want those things to be Lorentz invariant, I can build it as if A was a 4-vector, but the answer will only be Lorentz invariant if it's also gauge invariant, if it's invariant under this shift. And so this requirement of at low energies of Lorentz invariance with quantum mechanics is forcing on you this gauge invariant symmetry in the problem. So we ask kind of, if you ask what's the, we try and build what the Lagrangian would be for the most general effective theory that can describe a massless particle which has to have the symmetry, it turns out. Then we know that the things describing the kinetic, just the free propagation are given by the usual. The only thing that we can write down that's consistent with these, which has 2 derivatives and is consistent with the symmetry, is this particular term, and we recognize that as the Maxwell action. That says that this field, whatever it is, will be described by Maxwell's equations. And any coupling to anything else, say the electron, if we try and write something down like this, then what we know immediately is that because of the definitions here, F has to have dimensions of mass squared because the Lagrangian has to have dimensions of mass to the 4th. So A has to have dimensions of mass. So anything that's proportional to A in the Lagrangian has to have dimensions of mass cubed. And in order for this to be invariant under this gauge symmetry, it has to be a conserved thing. So we're looking for whatever we're going to couple A to, it has to be coupled to a conserved charge. So there has to be a symmetry in that sector, whatever it is, that A will be coupling to. And of course, that's, we know, is the electromagnetic symmetry, which is responsible for electric charge conservation. And we also know that electric charge conservation leads to a conserved current, and that conserved current has dimensions mass cubed. And so this whole thing has dimensions of mass to the 4th. And so the coupling we're going to be led to is going to be dimensionless. And so this is a kind of interaction that we can have at low energies because it's renormalizable. It doesn't involve any couplings with inverse powers of mass. So if my candidate matter is an electron, I've said this already. So if I take the special case where the matter is an electron, and so it's a spin-1/2 relativistic particle, which carries this charge, this conserved thing that that A is allowed to couple to, then the current I built from it is essentially unique. And I'm led to, this is the most general, renormalizable. This is the most general, if I ask kind of what's the most general interaction I can write down, which involves no couplings that are inverse powers of mass, this is the answer. There are 2 parameters in it because the things involving the derivatives, I can always rescale my fields to make them take special values. And I've chosen the canonical values here, -1/4 and -1. And then the remaining things have coefficients, and these are the coefficients. This has dimensions of mass because psi has to have dimensions of mass to the 3/2 to make this whole thing have dimensions of mass to the 4th. And then here's the only interaction I can write down. It's a special case of what I had in the previous slide, where this is now the electromagnetic conserved current for this symmetry that this system had to have. Psi had to be a complex field where I could rotate it by a phase in order to have this current. And so the most general thing I could have had at low energies is this, because there's no other interaction I can write down, which has only got couplings which are dimensionless or positive powers of mass. And this is quantum electrodynamics. So one of the remarkable things that you get from effective field theories, which is often not emphasized enough, is it provides an inevitability for some interactions that you can test many things at low energies, but there's not a lot of people testing whether or not Maxwell's equations are true at low energies, because there's a sense in which Maxwell's equations and QED are consequences of special relativity and unitarity in quantum mechanics, and that's it. And so there's a very little that has to go into the statement at low energies but what you have at low energies, let's say a charged spin-1/2 particle and a massless spin-0 particle that's interacting with unsuppressed at low energies, as in the Coulomb interaction. And that completely dictates the details of what's happening. So if I had a theory of the world in the standard model or in quantum gravity that produced an electron and it produced a photon, and then I found at low energies that it behaved like quantum electrodynamics, on the one hand, I can't claim much, because as long as I got the quantum numbers roughly right, I'm going to get the details completely right, because the effective field theory is telling you that the only way you can couple these things at low energies is in a way that looks like QED. That's great if I believe that QED is describing my experiments. What's good about that is that it means I don't need to care what's going on at very high energies to understand why QED is working so well. But if I have a theory at high energies, which I think I'm trying to test, it means that testing QED is not such a good test, because if I get anything roughly right, I'm going to get the details spectacularly right. And you'll see that when we talk about gravity, there's a similar thing that happens for gravitons, that if you get anything roughly right at low energies, you're going to get general relativity right. And so people don't, so that's great. If you believe that general relativity is describing nature, that means that's very robust and independent of details at high energies. But it means that if you also think that you know what's going on at high energies, say you have a theory of quantum gravity, it's not a huge success to get general relativity right. If you get just the gross features right at low energies, you will inevitably get general relativity right, as we'll see later on. So this inevitability of some things at low energies is very, very powerful, often underemphasized characteristic of vector field theories. Oh, I forgot to, I'm sorry, I forgot to turn.
Just one question.
Yes.
So is this also the fact that all this conclusion that we are having, that you also have a Fermionic field, then you have this mu Jmu kind of interaction. If you have a charged scalar field, then there could be another additional term into that, right?
If I had other fields, yes.
Yeah, the charged scalar field, complex scalar field basically. If I have that, then I have not only mu Jmu kind of term, but additional term in the Lagrangian, which is of course renormalizable. It just comes.
You're thinking of the mu phi term. Is that right?
Yeah, phi. Yeah.
Yes. Yes, those are certainly there. Yes, that's right.
Yeah. So just the additional thing is that no, I'm just asking. So what is we are having that this vector field? Okay, so it should if we require Lorentz invariance, then it should be gauge invariant, and the only renormalizable interaction that you can write down is this mu Jmu type. Okay, so I was just asking. This is maybe only for Fermionic field. If you have a complex scalar field, you could have one more term to that, right? That's what I'm.
That's right. Or another way to say that is that J mu might depend on A. So I should be careful what I say here, is that I did not intend to say that the only thing you can write down that's consistent with gauge invariance and renormalizability is A mu, J mu, where J mu is independent of A. That's not true, as you say. But what you do is that at low energies, you're looking for renormalizable interactions that are consistent with gauge invariance. And so the proper statement is, so what you would write down is, what are the most general renormalizable gauge invariant interactions? And those can be written the way I wrote them here, but then I should have written J mu can also depend on A if A carries the charge. And so actually that's not quite true. It's also true the scalar example you have also has J depending on A. So there's no requirement that the interaction has to be linear in A. That's true. But my conclusion is still true, though.
I may not be in mu Jmu form. Yeah. It may not be mu Jmu form only, the interactions. That's what I'm trying to say.
If you allow J mu to depend,
maybe yeah. Means it depends how you define Jmu, of course. Yeah.
Right. Right. I'm making an argument here that's really tailored to QED, because there we know that the gauge invariance makes it linear in A. But my final endpoint is a true statement that what you'd be looking for at low energies, it has to be a gauge invariant coupling of whatever the matter fields you think you have, coupled to A, and that's renormalizable. That should be dominating at low energies, and that is what's dominating at low energies. And in that case,
sure.
the counting of the parameters is the same as it was, as I'm telling you here, that the only thing that's ever appearing in the electromagnetic couplings is a dimensionless coupling at E. And it's true that the details of the operator form is different. That's true. That's a good point. Yeah. Okay. All right. So pushing on, what I started to do before I talked about the electron was to ask the same question for neutrinos. And you can kind of see how it's going to go through, because neutrinos, the only difference between neutrinos and electrons is that they don't carry electric charge. That's there is a conserved thing to which the photon couples. It just happens that neutrinos do not carry that conserved thing. And so given that, that means that the neutrinos will not appear in the current to which A couples. And that means that at the renormalizable level, they cannot couple to one another. And so if we go through the same exercise for them, for electrons and neutrinos, is the way I'm showing it here, this is the most general thing we could have had for if we only had one neutrino species at low energies. And you see that the neutrino is not doing anything. The neutrino has no interactions at all at low energies, consistent with renormalizability. Because it doesn't carry it, the only way it could have, given that the only things there are to interact with are other spin-1/2 particles and a massless spin-0 particle, the only way it could have had a renormalizable interaction would have been to carry electric charge, which it doesn't. That means that its interactions, the only interactions it can have at low energies have to be non-renormalizable, as they are in the standard model, or the Fermi interactions that we talked about before. And that means that it will inevitably be that they're very weakly interacting compared to the other things like electrons. And so there's an inevitableness to low energies that you don't need to worry at low energies that that some of the low energy limits of the standard model that neutrinos are weakly interacting are somehow sensitive, are fragile, and that if I change some small thing, I can all of a sudden get a bigger coupling to photons. You might worry that maybe I do a 15-loop graph, I can make neutrinos talk to photons in a way that is going to give them a bigger than bargained for interaction. That doesn't happen, and it doesn't happen on very general grounds at low energies. Okay, so the main message here is, which I'm probably flogging a little bit too much now, is that many features that we just take for granted around us in nature are really very general consequences of this observation that renormalizability is what emerges at low energies. It's not a fundamental God-given criterion, but it's something which is the automatic statement that if I'm at low energies, if I'm by assumption at energies low enough that I can ignore all possible powers of 1 over whatever the heavy scales are that I'm not looking at, if I can ignore them all, then what's left will be renormalizable, because that's what it means to be renormalizable. And that's a very restrictive thing to be renormalizable. And so you often don't have many options as to how you can interact in those kind of theories. And so it's no surprise that renormalizable theories also tend to be in systems that are well described, where there's big hierarchies of scale. We do find renormalizable interactions all around us describing what we see. So let me take a less trivial example. So far, all the examples I've been looking at in the standard model have been ones where we've integrated out the W and the Z particle. We're looking at lower energies than that. But we could equally well think of the W and Z particles to be in the low energy theory and integrate out heavier things. And so in the standard model, what's heavier is the Higgs and the top quark. So we could ask for what's the effective field theory when the Higgs and top quark were integrated out? What would that look like? And it wasn't an academic question back in the day, because back in the day, the W and Z particles were found in the early 80s, but the Higgs in the top, of course, took much later, much longer. And there was a very pressing question at that time as to what can we say about how heavy they should be? Where should we look for them? And what that essentially comes down to is asking, in this effective theory involving the particles that we did have access to then, W, Zs, and other things, what's the strongest way in which the top and the Higgs would contribute? Because observables that depend on that will be the ones that are most sensitive to their properties, and so will give us the most information about what their masses might be. And it was before they were discovered, people were fairly sure what their masses should be before they were discovered, using arguments along the lines of the ones I'm going to give right now. And so this is just, now what I'm going to do is just, I'm using this example because we always tend to talk about how the non-renormalizable interactions that are suppressed by masses are the ones that are negligible, but we often don't talk about the super renormalizable interactions that are enhanced by masses. So that the couplings that are proportional to positive powers of masses, they should be the most sensitive to high energy physics. When we say that heavy physics decouples, the statement isn't that all physics that is associated with heavy physics goes away. The statement is that there are some interactions at low energies that are more sensitive than others, because some of them involve positive powers of mass, and decoupling is really, in essence, a dimensional analysis statement. So if you're trying to infer properties of the top and the Higgs boson in this effective theory of W's and Z's and stuff in this effective theory below their masses, what you're looking for, or what you're most interested in, are the interactions that have the lowest dimension, because those will have couplings that involve the largest positive power of mass. And in that effective theory, the ones that have the lowest dimension are the boson masses. And the only bosons in that problem are the gauge bosons. And so the W and Z masses are the ones that have the lowest dimension. There's two of them, the W and the Z. And so these are the two terms that are the dominant ones, and that it should be the most sensitive to the properties of the top quark and Higgs. Now, you might say, well, that's true, but not so interesting, because we don't get to predict these masses. Normally, the masses, if there's a parameter in the Lagrangian, it's something which is it's a parameter. You learn what it is by measuring it. You don't get to predict it. And so, if I were to tell you that there's a quantum correction to these masses that involves the top quark or the Higgs boson, you might say, I don't care, because I didn't know what the thing was you were correcting anyway. And so all I'm measuring is the sum of all those things. So there's no real information in the fact that these masses are very sensitive to the mass of the top and the Higgs. And that part is not true in the standard model, because in the standard model, if you think about where these masses came from, they came from one term. In the standard model itself, the thing that had the Higgs and the top quark in it, both those masses came from the Higgs kinetic term. They were both buried in there. So there's one effective operator that gave you two masses. And that's why the standard model gives you this prediction that the W mass and the Z mass are related to the weak mixing angle. And so as soon as you integrate out the top quark and the Higgs boson, the effective theory below those masses is no longer gauge invariant in the SU2 cross U1 invariant way. You remember that one of the lessons of the toy model was the symmetries of the full theory are always there, but they may be realized differently at low energies compared to at high energies, particularly if the symmetries relate particles that were heavy to particles that were light. In the standard model, the SU2 gauge interactions relate, say, the bottom quark to the top quark, and we're going to keep the bottom quark in this effective theory, but get rid of the top quark. So those are symmetries that are less informative than they once were. And so in this effective theory, we no longer have the constraints of linearly realized SU2 cross U1 invariance. And so we no longer are required that these masses will be both coming from one interaction in the Lagrangian. And so the prediction we get to make is deviations from this prediction that came from the standard model. And those are present. And so if I calculate the self-energy of the W and Z bosons, for the Z boson, I'd have a top quark loop here, or you could imagine having a Higgs loop here. That second thing is not right. There's a different calculation you do for the Higgs, but it's related to this. But for what I'm saying now, to focus on the top quark, if I have a top quark loop with two Zs on a Z on either side, or I could have a Z and a photon on either, a Z on one side and a photon on the other side, or I could have a W boson on both sides with a top quark and a bottom quark going around the loop. If I do those things and I calculate the corrections to this mass relationship, it turns out to be proportional to this product, and it's given by this expression. And as advertised, you might have thought that since the masses are dimension 2 interactions, coefficients are quadratic in mass, because that's why they have dimensions of mass squared, not accidentally. And so they should have been sensitive to the heaviest scales in the problem quadratically, and they are. So this graph gives you a correction to those masses, which is proportional to the top quark mass squared. And it's something which is observable because it can be this particular combination is something which is a violation of this standard model prediction. And so because of that, it's a measurable change in the W mass. If you fix the Fermi constant and the weak mixing angle, what you're doing with this correction is changing your prediction for the W mass. And in the standard model, that was a prediction. And so it's measurable. The deviations from that are measurable. And so there's a similar story for the Higgs, except the Higgs turns out not to give you anything quadratic. You might have thought you would have had a quadratic Higgs contribution too, because it's also heavy. Turns out there's an accidental symmetry in the standard model, what's called custodial symmetry, which forbids you getting a correction that changes these masses. But there is a correction to the kinetic energies of the gauge bosons, which gives you a logarithmic dependence on the Higgs mass, which you can track in as easily as you can track this. And this is although doing radiative corrections in standard model is a complicated business if you're going to do it right, tracking things like the heavy mass dependence is actually surprisingly easy because of the simplifications of the effective field theories. And so that's kind of a historical example that is probably less well known now because we're no longer in the situation where the top and the Higgs hadn't been produced yet. Okay, so that's the standard model story. Let me confirm how much time I have here. I want to make sure I got the time change right.
Yeah, it's up to, 3:30. So you have more than, like 40 minutes you have.
40 minutes. That's okay. That sounds right. So let me just reset. I forgot to start my clock when I started here. So let me just make sure I have that set properly here. Okay, good. All right. So I should probably pick up pace a little bit here. I'm going to very quickly go through substructure. The main message of this section is that the standard model also teaches us that there's nothing that requires the particles involved in these effective theories to be elementary. Classic example is in strong interactions. We know that quarks and gluons are not appearing all around us in nature. Hadrons are, nucleons, for example, and pions. And what's going on in the standard model as a quark process, for example, where a pion is emitted by a nucleon, in an effective theory where you can't resolve the nucleus, so you're looking at scales larger than a Fermi or energies lower than a few hundred MeV, these things are going to look like elementary particles. And in the point of view of a Wilsonian action, where you're thinking of effective theory as being something you got by integrating out stuff, there's nothing fundamental about your field content. All you really are looking for are fields that describe the degrees of freedom that are around you. And in the case of low energy QCD, where you're looking at hadrons, the fields that will appear in your effective theory will be hadrons. But the whole rest of the story will go through as before. You'll take your effective theory involving the hadrons, and you'll match it to what you know about the properties of QCD involving quarks. And it may be difficult to do those matching calculations, but if you can find a way of doing them, then the arguments of the effective field theory go through just as before. And there's a famous case in which that was done because the predictions depended just on symmetries, not on detailed calculations of QCD. And again, this goes back to Weinberg. This is one of those places where that led to the development of effective field theory techniques called chiral perturbation theory. So in QCD, there's a famous symmetry where you take the up and down quarks, left and right-handed, and rotate them by unitary matrices independently. That's an SU2 cross SU2 symmetry. And the vacuum of QCD spontaneously breaks that down to a diagonal subgroup, which is isospin, where you rotate left and right-handed fields together. The Goldstone bosons for that are not exactly Goldstone bosons because it's not an exact symmetry. The quark masses break the symmetry. And so, but in the limit that the quark masses had been zero, the Goldstone bosons for that should have been massless. And those Goldstone bosons have the quantum numbers of pions. And in QCD, that's the explanation for why pions are so light compared to the other scales. So the typical scale of the strong interactions is a ballpark of a GeV or 500 MeV. Pions are down at 100 MeV. And the reason for that is that if you'd made the quark masses zero, they would have been massless. And so because they're Goldstone bosons, their interactions, as in the toy model, are completely governed by the symmetry breaking pattern that they're associated with. So it turns out that at the two derivative level, at low energies, that statement I made is true. We know that as Goldstone bosons, they're going to want to interact derivatively, much like in the toy model. And so it turns out that the pions, there's three pions, a charged one and a neutral one, which you could think of as being three real fields. They, at low energies, the symmetries require them to interact at the true derivative level through a Lagrangian like this, where there's some coefficient function here, and there's some normalization f. But the important thing is that this coefficient function, its form is completely dictated by the symmetries, and so it turns out to be you can write it in this way. So what that means is that at low energies, pions are going to have scattering properties that are completely governed by one parameter, f. If I canonically normalize these fields by scaling f into the field theta, then I'll be led to a Lagrangian involving pions whose scattering I can look at, but all the various interactions, if I Taylor expand G in powers of the pion field, all the interactions here are all involving just a single parameter. So if I write that out the first few turns, it turns out to be this. And once I've canonically normalized things, then the f goes into the denominator. What was theta before is now pi over f. And so each term here, each term in this expansion involves two derivatives exactly, but more and more powers of pions fields and more powers of f. And so that means that there's going to be a whole bunch of things that are relationships amongst these scattering amplitudes because they only depend on one common parameter. And those relationships are called soft pion theorems, and that's kind of one of the successes of this chiral perturbation theory story. And of course, it's better than that because that value of f, turns out you can measure it in pion decays. And so you can independently measure f through a non-scattering process. And so not only is there one parameter, you know what the value of the parameter is. And so this is a huge success of QCD that is one of the ways in which the robustness of effective field theory techniques was developed. The fact that the effective theory involves composite degrees of freedom, and that the underlying theory was strongly coupled, that was completely irrelevant for the success of these effective field theory arguments. There's another sense in which composite things commonly come up in life, which you've probably done already as an undergraduate. Any composite body that, if you're looking at it on scales that are so large compared to the size of the object and the energy scales of the object, looks like a point particle to you. That's an effective description of that object. It could be the Earth. When you're talking about orbits of the Earth around the sun, you typically idealize it as some point particle where all you assign it is a mass and a position. And that's because formally, if you had theory of the Earth, you could have imagined integrating at all the internal degrees of freedom of the Earth and just be left with its center of mass position, which is guaranteed to be there at the low energies. There's a sense in which the center of mass of the Earth is a Goldstone boson. The flat, space has translation symmetries, and the presence of the Earth breaks them. And so there's a sense in which there's a collective coordinate in the Earth, which is describing the way in which the presence of the Earth breaks an underlying translation symmetry. So there has to be, in the low energy theory, a Goldstone field for that, and that field is the center of mass. And if you ask kind of what's the low energy description of that, it's what you would have typically done, you would have written down anyway if you were trying to write down the Lagrangian of a point particle, right, which is described by whose only degree of freedom is its position. And so there's a sense in which all of the non-field theory quantum mechanics that you do can be thought of as an effective field theory for the standard model, where you've integrated out all the stuff except for the center of mass of the particle of interest to you in any given application. And it's more than just at the leading level. In this kind of expansion, these higher terms have interpretation in terms of the physical properties of the object that you're talking about. In this particular one I've written down, this is an electric field squared. This coefficient would be the polarizability of the object, and various multipole moments would appear in this expansion. And they are the things that are, as you got better and better resolution of what's going on, are the things that are dominating the way that external fields will respond to that source. So there's a sense in which we've all been doing effective field theory since day one on our mother's knee, and just weren't systematic about it. This is useful because when it comes to time to do very precise calculations with atoms, this way of thinking of things allows you to take all the machinery of bound states for atoms and then match it on to the quantum field theory machinery of radiative corrections, for example, in quantum electrodynamics, and mesh them together in one seamless picture, so that you're not trying to splice hammer a quantum field theory calculation involving radiative corrections of something onto, not trying to shoehorn it into a description of atoms using non-quantum field theory language. There's really a language that includes both those things, and you can really systematically calculate the contributions of relativistic effects and on things like atomic properties or orbits. And this is being developed now for gravity in great detail with the discovery of gravitational waves. Very efficient way to think about things. Related to that is the whole story of non-relative. So previously, looking at center mass as kind of one particular feature of low energy systems, but I wrote those that effective description relativistically, and there's no reason why you need to do it relativistically. Typically, for the example of the Earth, you're not thinking of a relativistic Earth. You can actually, that example shows you that you can look at effective limits where the particles that are in them are actually much heavier than the upper, what you thought of as being the dividing line between low energy and high energy. So the next examples I'm going to talk about are examples like that, which are called non-relativistic effective field theories. It's cases where the actual rest mass of the things in the low energy theory can be actually very high, like the mass of the Earth. That's enormous in GeV. But it can still be true that the energies that are available to the dynamics are only the kinetic energies. And so you can't liberate that rest mass. And so it can be true that you can describe the effective motion for a theory involving particles that are very massive compared to what you thought your cutoff was. So this is just saying what I just said, that it sounds paradoxical that you'd ever have an effective theory where you had a non-relativistic particle in it, because that particle would have had a mass much bigger than your cutoff, and so it should have been one of the things you got rid of. It should have been like the heavy field chi in the toy model. And the way around that is if you're in a situation where the energy in the rest mass, which is enormous in this low energy picture, if it's not available to be liberated, then it's possible that you could set up for have long times for which other low energy effects are important, and the rest mass is just irrelevant to any of the dynamics. That kind of thing happens if the particles involved are stable. So it tends to be that that you're talking about in the case of the Earth, the baryons number conservation keeps things. I see that somebody's writing something on the screen here. Is there a question?
Rosalind is writing something, so I think you can go ahead. I believe there is no question.
Sorry.
Okay. I don't know if anybody can get. Probably that'll remain there as I keep going here, but it's. Anyway, the bottom line is that the typical ways to avoid having the rest mass be released is to have the particle be stable. Maybe it's the lightest particle. You might work instead of working in the vacuum sector of the theory where you're looking at low energies, you could work in the vacuum sector of the piece of the theory which has baryon number 10 to the 26, and then the lowest energy state there might be a solid which has a lot of baryons in it. And so the baryons, because they're stable, they wouldn't have released their rest mass, and so it makes sense to do condensed matter physics in that kind of a situation, for example. Another thing you have to be careful of is you don't want to have a lot of antiparticles around, because if antiparticle, even if the state system is stable, if you have particles and antiparticles present, they can annihilate, and that will release a lot of energy. So if you're going to do this, it has to be true that you can sometimes have particles and antiparticles, but they have to be in a way that they're sequestered from one another. So they find each other only very rarely. And I'm going to describe an example where you can include both particles and antiparticles when looking at positronium in a second. Okay, so the main generalization here to the effective field theory story is that the conservation, you might use more than just energy conservation to define your effective theory. You might also use some other, you might want to have a fixed electric charge or a fixed baryon number or a fixed lepton number as also a subsidiary condition defining your effective system. But apart from with that proviso, everything goes through like I described it. If anybody can figure out how to get rid of this, the doodling, that would be great.
Yeah, so I mean, Rosalind, or can you delete it, or I mean, organizers, can you erase it, this marking?
Anyway, while you're thinking about that, I'll press on. So from the point of view of the effective theory, the main thing that happens when you go below the threshold you go below the mass of a particle to make it non-relativistic, the main thing that's happening, if you want to think about what you're integrating out, it's the antiparticles. If you expand a field, a relativistic field in terms of creation and annihilation operators, there's a particle piece and an antiparticle piece, and they always come together in this destruction and creation combination. And so that's not true in non-relativistic systems. In non-relativistic systems, you can take fields and write them in terms of just destruction operators. You don't need to have the creation part of the antiparticle there. And that's because there's no requirement. These things are here because you want fields to commute at space-like separations. And that's one of the things you ask in order to have things that are space-like separated be independent, evolve in a statistically independent way. So one way to think about what's going on when you go to the non-relativistic limit is that you can think of your relativistic field as having a particle part and an antiparticle part, and you're going to integrate that guy out. But while you're doing that, it's also useful to have the zero of energy not be zero. If you're going to not be able to release the rest mass energy, you might as well make the zero of energy the rest mass. And so it's also useful to redefine your field by scaling out a factor of e to the minus IMT, where m is the rest mass, because that will make that effectively makes the zero of energy it makes m the zero of energy rather than the zero of energy. So this is the kind of redefinition you do, and there's a conventional factor up front here which I'm sticking in just to arrange that once I'm finished, the time derivatives of phi will be recognizable. You'll see why in a second. So if I take say the Klein-Gordon action and I do that exercise of writing phi in the way I just described, then what happens is that the time derivatives of phi give me a minus m squared phi squared, which cancels the m squared phi squared. And remember, m is a large scale, so we don't want pieces in our Lagrangian that are big at low energies. We want things that are suppressed. And so that change of variables that puts the zero of energy by pulling out the factor of e to the minus I mt, removes that m squared, and what's left becomes a single time derivative of phi is the thing that involves the fewest time derivatives. And then the thing with the fewest space derivatives has got two of them because of rotational variance. And so you recognize this piece and this piece as being the first terms in the Schrodinger action. And what you're led to in this way, as you integrate out the antiparticle, is the Dirac action or the Klein-Gordon action lead you to the Schrodinger action, and you're led to the many particle quantum field theory of non-relativistic many body systems in a very systematic way. This has been used in particle physics in HQET, for example, in describing the presence of heavy quarks, which I will not talk about, but I just mentioned in passing. This is kind of the formalism that you're using. And what complicates non-relativistic discussions is that there's more than one low energy scale. You know, when I was doing the power counting yesterday, I assumed there was only one scale Q at low energies, and there wasn't a hierarchy of scales that are all at low energies. In non-relativistic systems, you always have a hierarchy of scales, because if m is the heavy scale, the momentum is much less than that if you're moving non-relativistically. It's suppressed by the speed because it's mv, but the energy is then suppressed by 2 powers of the speed because it's down by another power of m. And so your kinetic energy and your momentum, additional powers of v, are all hierarchically new scales that are all low energy scales. And so that complicates the power counting story for non-relativistic systems. And so when you look at non-relativistic effective field theories, you'll see that their rules for counting what's there is more complicated. And it's because of this, that you're dealing with that you fundamentally have multiple low energy scales. And so dimensional analysis by itself isn't enough because you're trying to keep track of the powers of the dimensionless factor v, which is small. Typically in an atom, v is of order alpha. So if you're keeping track of alpha effects, the fine structure constant, you need to keep track of powers of v. But apart from that, you can now do once you keep track of that carefully, you can do the matching story you would have done. And now the full theory would be the relativistic system, maybe QED, and the effective theory will be this non-relativistic Schrodinger picture. And you can match the coefficients the way that you normally do. You take some simple observable, calculate it in the full theory and in the effective theory, and demand that the coefficients in the effective theory give you the same answer. And if you do that for a non-relativistic particle coupled to electromagnetism, you get what's called non-relativistic QED, and the thing involving no powers of the heavy mass. This is all you get. It's just basically the electrostatic coupling of the field, and then the thing involving one power of mass in this way involves the coupling, the kinetic energy, but it also involves the dipole coupling to the vector potential, and the Pauli term if you have a spin a half piece, plus an a squared term, which was alluded to earlier on in the questions. At second order, you get a bunch of other terms that you recognize. There's a Darwin term, there's the spin orbit term, and there's various contact interactions. And so all of these things I've written with coefficients, CS and CD and D1 and D2 and CF. And those things are the ones that you would determine by matching. And I've pulled out factors of the charge of the particle and the mass such that at lowest order, these C's will be 1. But in principle, they will get corrections which are order alpha. For example, the order alpha correction to CF will be the anomalous magnetic moment. And if you want to see how the anomalous magnetic moment shows up in atomic energy levels, this is how you keep track of it. So for example, if you match these graphs in the full theory onto that theory I just gave you, you learn that these CF, CD, and CS, so this is the Darwin term, this is the spin orbit term, and this is the Pauli term, have these corrections at an expansion to order alpha. At tree level, you would have had just the vertex correction with no loop correction. That's the 1. And then that's why the factors of E and M were taken out. So now if you apply that, now you can take that thing as usual effective theories. It doesn't matter where you get the interactions. You can use them in any observable you like. And so now you can go off and calculate something more complicated, like energy level shifts. And so here's an example of that. If we take positronium, where I have a non-relativistic electron and a non-relativistic positron, stick them in an atom. So it's a Schrodinger, it's a hydrogen-like atom. Even though there's a particle and antiparticle, we can do that because they are mostly not near one another, so they don't annihilate very quickly, but they can annihilate very slowly, and so the theory should tell us that. So in that case, I'll have 2 fields. Psi will be the electron field, and phi will be the positron field, and these sigmas are Pauli matrices. And that quadratic contact interaction I showed you now, there's a version of it which involves 2 electrons and 2 positrons, which I'm going to focus on. It has, so the coefficients here are called dV and ds because unlike the previous case, everybody is not an electron here. Now there's 2 electrons and 2 positrons. Same kind of a story about matching. If I take these various graphs and some other ones, and I match, I learned that these coefficients ds and dV are given by this to order alpha squared. And I tell you that because there's this interesting piece that is imaginary, which is that doesn't normally happen. This is a sign that there's the system's unstable. This graph here is what makes this thing imaginary. This is the graph that knows about positron electron annihilation. And so this imaginary part is a reflection of the fact that these particles can annihilate. And so when they do, they remove probability from our effective theory. And so that's something which is going to look like a non-Hermitian Hamiltonian. But it does so in a way which is very specific. You have to have some density of electrons and positrons talking to each other for it to happen. It's not like the whole Lagrangian is all of a sudden complex. So given this Lagrangian, you can just use ordinary Schrodinger non-relativistic wave function arguments to figure out energy levels just using Rayleigh-Schrodinger perturbation theory. And an example of that using these coefficients dV, ds, and these coefficients CF, CD, and CS. If I focus on the spin-dependent parts of the energy, because I'm going to look at the hyperphi splitting, let's say, so I look at the spin 1 versus spin 0 pieces where the spins align or anti-line. They depend very generally on these coefficients, CF and dV. And I put in the values that I got from matching, and I got the matching, remember, from doing some scattering calculation that was simple. Then I learned that this becomes a very specific function of alpha because these CF and dV are now written in terms of alpha. And this is a famous result for what not only the leading hyperfine splitting is, but also the subleading contribution to it. And it's obtained much easier than it is done using the full formalism of QED applied to the atom, because you can use ordinary Schrodinger techniques for the atom. Same thing for the imaginary part. If I look at the imaginary part of the energies, I'm learning about decay rates. And so if I look for the decay rate of the spin 0 combination, I find it's the imaginary part of this combination, and for spin 1, it's the imaginary part of that combination. And if I put in the values of ds and dV from the previous slide, you get that the first one is what's shown there, and that's the famous alpha to the 5th decay rate of that. I can't remember if that's ortho or parapositronium, but that's the one that decays, and the other one doesn't decay at this order at alpha to the 5th, and that's because there's a selection rule, charge conjugation, that forbids it from happening at this order. You have to go to higher orders, and so you can reproduce in very simple ways detailed things, including higher order corrections in alpha, because of the efficiency of using ordinary Schrodinger techniques for the non-relativistic bound state part and combining them with the complicated the different relativistic radiative corrections that you do in the relativistic part, and the matching tells you how they relate to each other. So it's very efficient way to do very precise predictions for bound states. So in the last 10 minutes, I think I've got 10 minutes left. I'm going to talk about gravity a little bit, and then we'll close off. So I just first going to start off just repeating what I did for the photon. So the massless spin 2 particle is actually just not described by a symmetric tensor. It's described by a rank 4 thing, which is essentially the Riemann tensor, which is the field strength for a spin 2 thing. But it's the condition that it described a massless spin 2 thing means it's 2 derivatives of something else, which is this thing, the symmetric tensor. It's not really a tensor because if I do a Lorentz transformation, it's a tensor up to a shift of this form. And so there's a gauge invariance that has to be present if I want to have interactions that are not suppressed by derivatives. And the same story that I told you for photons goes through in a slightly different way. The free action has to be this particular combination. That's the only thing that's invariant under the gauge symmetry. And again, the leading coupling, and again, the same assumptions, the same discussion that we had about electromagnetism is true here. T mu nu might depend on H. But if I ask what's the leading coupling, so the thing that starts off linear in H, the coefficient has to be a symmetric tensor. Again, on dimensional grounds, H is dimensions of mass. But we're looking for a symmetric tensor that has to be conserved. It has to be conserved in order for this gauge invariance to be true. And the Coleman-Mandula theorem in relativistic quantum field theories tells you that there's a unique thing that does that. That's the stress energy tensor. And the stress energy tensor has dimensions of mass to the fourth, because it's an energy per unit volume. And so that means that this whole thing has dimensions of mass to the fifth. And so this coefficient has to have dimensions of inverse powers of mass. So in the spin 2 case, the same argument that in electromagnetism told us that QED was the generic renormalizable answer, it tells us that for a massless spin 2 thing that couples to stress energy, that has to couple to stress energy. So anything that's coupling to stress energy, that's long range, and it's not vanishing in a zero derivative, when derivatives are small. If you ask what renormalizable interaction should emerge there, the answer is there are none. And so we shouldn't be described to find that if a graviton is around at low energies, it's going to be very weakly interacting. This doesn't tell you that it should be more weakly interacting than neutrinos. The fact that the Planck mass is larger than the Newton's constant is smaller than the Fermi constant isn't coming from this. But the fact that it had to be non-renormalizable in the interaction is inevitable, given that it's massless and spin 2. Okay. You can also repeat the argument about you can do better. You can ask kind of how do things behave at the 2 derivative level, and that's those symmetries are sufficient to dictate what those couplings are, and those are the couplings of general relativity. There's an old argument by Weinberg and by Deser independently, which shows that if you bootstrap this up to ask how would the HB nu interact with itself under the assumption you only involved 2 derivatives, what's the most general thing you get? It's the general relativity, essentially. And so that's normally written as in terms of the curvature of the metric. If you write the metric in this particular way for an expansion around flat space, where this is the Minkowski metric, then if this is the Ricci curvature tensor scalar, then this turns into this expansion, and it has very much a chiral perturbation theory form. Lots of terms involving all different powers of h contracted in different ways, and I haven't written the indices here, but they all have 2 derivatives exactly, because curvatures always involve 2 derivatives of this metric field h. So if you go through the exercise of calculating scattering, say of gravitons in this way, the same graphs at tree level appear as we had in the toy model, and they give you can kind of see that every interaction has got two derivatives in it. So we should expect to have something like we had in the toy model case. We're expecting to get something which involves 2 powers of energy. It was 4 powers of energy in the toy model case because the propagator here was a massive propagator, but in this case now that's a graviton, so it's got a 1/q² in it. So we get something which is only suppressed by 2 powers of q. And if you do the calculation actually exactly as DeWitt did, this becomes the Mandelstam variables S, T, and U. And so the energy squared is coming to you as this particular combination of energies and angles. And G here is Newton's constant. And Newton's constant, if you ask what the equations of motion are for the metric, you can relate the Planck mass to the phenomenological Newton constant. And 8 pi G is 1/m Planck squared in that correspondence. Now, the problem that with gravity is that people have when they think about it quantum mechanically is usually phrased that it's not renormalizable. And the way that shows up is if you do corrections to what I just described, each of these interactions has a 1/m Planck. The trilinear ones, remember, they have a 1/m Planck. They have 2 derivatives in them. And so I'm going to get a 1/m Planck to the 4th in this graph. There it is. And I'm going to get 2, 4, 6, 8 derivatives in the numerator coming from the derivatives of the interactions. And I'll have 4 propagators going like 1/p² plus external momentum q². So I'll get something schematically like this. There's a loop integral, and I've got a total of 8 powers of momentum in the numerator because there's 4 vertices of 2 each. At least 2 of them have to be in the external momenta because of gauge invariance, it turns out. So the remaining 6 could be inside the integral. They could be the loop momenta. And if I do the same thing for a higher loop graph, I get a similar thing where now I have 1, 2, 3, 4, 5, 6 powers of 1/m Planck, which I've actually written wrong here. I figured this should be m Planck to the 6th. I have to have at least 2 momenta coming from q². If I count all the p² from the vertices, the rest would be here. Altogether, there are 12, so now there's p to 10 here. And you see that what's happening is that each of these integrals is more and more divergent. If I cut it off at some scale lambda, they're more and more divergent. They're diverging like powers of lambda. But because they all go like q², I can think of them as being corrections to what I had on the previous slide, where Newton's constant is being corrected in a lambda-dependent way. So that actually sounds very much like in quantum electrodynamics. The thing that's different about gravity is sometimes the answer is not just proportional to q squared. It involves q to the fourth and q to the sixth, because some of these other momenta, you can have more than two of the momenta in the numerator being external momenta. And these things that involve q to the fourth, they still have divergent coefficients, but they can no longer be absorbed, those divergences, into the Newton's constant, because you know that Newton's constant at lowest order just gave you something going like q squared. So that's what it meant to be not. The problem there is happening because the coupling constant has got dimensions of inverse powers of mass. You stick a lot of them inside a graph, and then on dimensional grounds, you've got lots of momenta in the numerator to compensate, and so you get more and more divergent answers. And of course, the way out of that is this effective field theory way out of it. We shouldn't be restricting ourselves to just Newton's constant, because that's only one term in the effective Lagrangian. I'm going to skip. This is just a rationale about why this is a rationale about why you should care. And the message is that gravity is a precision science, and so knowing the size of your errors is very important if you're comparing to experiments. So we should be thinking of writing down an effective Lagrangian involving all possible combinations of the fields at higher and higher derivative level, but consistent with that symmetry that made the particle a massless spin-2 particle. And that amounts to a curvature expansion in this case, where there's a bunch of terms. Every R here, all you need to know about it is that it's built out of a gamma, and gamma is built of the metric. It's either the inverse of the metric or the metric, and gamma has one derivative in it, and so R always has two derivatives. It's either the derivative of that or it's the square of that. And so each term involving R here has each additional R means two more derivatives of the field. The other thing I'm going to come back to probably is that the scale appearing in front of these higher derivative terms, people often write it as being the Planck mass, but it's almost certainly not the Planck mass if you think about where it came from. Now, if the smallest mass wins in the denominator, if you sum over a variety of particles here, the smallest one will win in the denominator, whereas the largest one wins in the numerator. I'll come back to that. If I now just repeat the exercise that I did in yesterday about power counting that, there's a bunch of interactions, they all depend on scales in a particular way. I stick them in some graph with E external lines, and I just do literally what I did in that case. I can specialize what I showed you there into this example. If I just read off what the scales, I remember I had some scales mu, capital M, and V. They are all related to M Planck and to little m and so on. And you get, this is what you get for gravity. If I take graviton scattering and I ask which of these interactions appears at what order in the energy as a function of energy for a graph with E external lines and L loops involving V vertices, where V each vertex has I fields joining there and K derivatives. So K powers of momentum. This is what you happen to get. Little m here is this coefficient in front of these higher powers of R. And capital M Planck is the Planck, and Q is the external energy. So this tells you, for any scattering process for gravitons, how big any contribution in this whole thing, not just from general relativity, but from everything, how big it is. And in particular, general relativity is a special case of interactions which have two derivatives. So now let's ask, what's the dominant contribution to this amplitude? Well, the dominant contribution comes, there's always positive powers of Q divided by these big scales. So if I make this 0, so I take L equals 0, that'll win. I'm stuck with this factor because it's just fixed by E. If I have 4 E's, if E is equal to 4, so for graviton scattering, this will be 2. So I have Q squared over M squared. And then I should take these V's, and you notice that the product here is only over interactions for which there are more than two derivatives. So one way in which I can make this whole thing 0 or not be suppressed by Q over M is to take V equals 0 for all the interactions that have more than two derivatives. So what is that? That says I'm supposed to take all the tree graphs, L equals 0, corresponding to the terms in the Lagrangian with exactly two derivatives, that is to say the general relativity Lagrangian. That's general relativity. It says that the dominant contribution in this expansion is classical general relativity. That's something you might have believed anyway, that classical approximations in gravity should be good. But this tells you how big the corrections are. It shows you that the corrections are the next biggest thing that has the least additional suppression. I either take L equals 1 and continue to take V equals 0 here, so that would be one loop graphs built using general relativity, or I take L equals 0 and I let one of these V's be 1, but only for K equals 4. So I only take 4 derivative term, which is a curvature squared term, and I take exactly one insertion of an interaction from that, and that will compete with the one loop general relativity. And that'll be suppressed by 2 powers of Q over M Planck. And what's happening is that those curvature square terms are exactly the guys that need to be renormalized to keep track of the divergences that you were getting from the one loop graphs in general relativity, and so on and so on. If you decide that the accuracy of your calculation is sufficient to work to one subdominant order in Q over M Planck because Q is sufficiently low, then that's all you ever need to do. And so the only new parameters you need to keep track of are M Planck, C1, C2, and that's it. And as long as you have measurements that will tell you those coefficients, then you can predict everything else. So the predictivity of gravity is good. And this shows you that the classical approximation in gravity is the low energy approximation. So if you want to use classical techniques in gravity, the justification for it is that you are using a low energy expansion. So you have to be careful that you don't lose control of the low energy expansion whenever you do gravity, and in particular cosmology. So where do these terms come from? I'm just about done. Where these things could have come from, you know, I mentioned before, the analogy with the weak interactions is if there were states that were very heavy that had renormalizable interactions that were being exchanged, they could look at low energies like a non-renormalizable interaction like the gravitational one. And so you might imagine that you integrate those things out. There will be heavy things that will contribute external gravitons, and those typically do give you interactions like this. So you should expect that these M's here are probably the masses of the things going around the loops. And so you're probably going to get sums over the things that were in the loops. So some sums over the different masses of who could have been in the loops here. And that's why I'm telling you that the smallest mass that could have been in the loop is probably the one that wins in that sum, because your sums of terms that are all going like 1 over m squared will be dominated by the smallest m in the problem. So now I'm at the last slide. So the bottom line is, I hope you're convinced that effective field theories are super, super, super useful. They are the difference often between being able to do a calculation and not being able to do a calculation. And the reason they work is that you make the low energy expansion as soon as you can in the process of calculating anything. So you reap the simplicity as early as possible. And you do that by writing down the expansion in the action itself, and then you calculate any observable you like with it. And the example I've chosen have been designed to try and show the robustness and the versatility of those tools. They're not just restricted to the weak interactions. They apply to everything. They apply to gravity. They apply to non-relativistic systems. They apply to point particles. They apply everywhere. And they come with it some very important conceptual benefits. They tell us why many of the interactions that we see around us work. General relativity is the only known way of coupling a massless spin 2 thing to anything at low energies. Maxwell's equations are the only known way to couple a massless spin 1 thing to anything. The Standard Model is the only known way to couple the particles with the quantum numbers under the symmetries that we know about at low energies to themselves. The Standard Model is the most general way you could do that. Those kinds of there's an inevitability to those kind of theories. Often it's said that the Standard Model is not a beautiful theory, and that's true. But it's beautiful in this. There's a very precise way that it's the most general thing that's consistent with the low energy interactions of particles with those properties. And many of those insights at many levels came from Weinberg. The effective field theory construction, the systematization of it itself, the observation of how the low energy fields and our massless fields are strongly restricted in the ways that they can interact. The observation that quantum field theory has very little content intrinsically to itself beyond building in things like cluster decomposition, the power and the almost inconsistency of quantum mechanics and special relativity. Those really are part of his legacies. And we run a series called All Things Effective Field Theory, in which he gave the inaugural lecture. And he was talking about the history of effective field theories. And in it, what's striking is that in the 60s, he felt very much like an outsider. People were doing S-matrix theories, and he was pressing on with quantum field theory. And in the end of the day, his point of view is now the zeitgeist. It's really has survived and blossomed and become incredibly powerful. And it really behooves us to use the simplicity and the insight of these techniques, because it makes our lives simpler. And so I hope you really will use them in whatever you choose to do in your physics career. So thank you for listening.
Thanks for a very profound talk. I mean, are there any questions?
I have a question.
Yes.
Go ahead. Yeah.
Yeah, in general, in EFTs, when you're dealing with the W and Z or gauge theories, people generally assume that in the EFT you can lose gauge invariance. We find as long as you restore it in the full theory. For example, like studying in the kappa framework, studying deviations in the W and Z interactions with the Higgs.
Yeah.
I'm just wondering that because gauge invariance or gauge is not a real symmetry, it's more of a redundancy. It's an artifact that you introduce to begin with. Is this something that is consistent, or can you say that you shouldn't have any of these deviation, or you shouldn't lose gauge invariance because it's a redundancy to begin with?
I would say it's a kind of a bit of a wording issue whether you think of it as a redundancy or a symmetry. But I would agree that the statement about the statement about loss of gauge invariance is really a statement about spontaneous breaking as opposed to explicit breaking. And for global symmetries, there's a real distinction between explicit breaking and spontaneous breaking, because explicit breaking is when the Hamiltonian is just not invariant, and spontaneous breaking is when the Hamiltonian is invariant but the vacuum is not invariant. And the difference is there's a physical difference in those two things, because in the case that you spontaneously break, the Goldstone bosons are around in the low energy theory to tell you that in whatever happened, the symmetry you're talking about was spontaneously broken rather than explicitly broken. And the issue for gauge series is that that distinction is no longer there. That for gauge series, it's essentially the statement is that a spontaneously broken gauge series at low energies is indistinguishable from a explicitly broken gauge series at low energies. And that's the sense in which the redundancy makes complicates the story of symmetries. And so so the sense in which is different, that it's a redundancy. So what that means operationally is that you've got two ways of thinking about gauge series at low energies, where the energies are below the masses of the gauge bosons themselves. So you're in a regime where you've spontaneously broken the gauge symmetries. And these are completely equivalent ways of thinking about it. One of them is I can just think of all the broken gauge symmetries as just not existing. So in the standard model and the effective theory below the W's and Z masses, I would just say my gauge symmetries is SU3 color cross electromagnetism U1, and that's it. And then I just explicitly break the SU2 cross U1 invariance. The other way of thinking about it is you say, well, I actually have the full gauge theory of the standard model, but I non-linearly realize it in the same way that we did in the toy model, where we just have it act on the Goldstone bosons themselves. And what you can show is that those are the two different ways of describing the same thing, because the explicit breaking is the unitary gauge version of that non-linearly realized story. So the lesson at low energies is that if somebody breaks a global symmetry at high energies, you know about it at low energies because the Goldstone bosons are there to tell you. But if you break a gauge symmetry at high energies, then it's gone. And so at low energies, you've lost that information. The only thing you know is that if you have a massive spin 1 particle or a massive spin 2 particle, something that would have had to have a gauge symmetry if it were massless, the scale where the effective theory breaks down is much, much closer to you than it would need it to have been if you had had a gauge invariance, a linearly realized gauge invariance. And so the arguments that for the LHC said that if there was no Higgs, for example, unitarity was going to fail at the TV scale. That was happening because you didn't have the gauge invariance that was building in the consistency of the effective theory up to arbitrarily high scales. It was really had to fail at the TV scale because of the absence of gauge invariance. I'm not sure if that answers your question, but the way I've phrased that at the absence of gauge invariance is that it's certainly true that once you go below the gauge boson masses, gauge invariance essentially effectively is not present. But the unitarity scale, the effective theory has to break down at a scale of order the gauge boson mass divided by the coupling, gauge boson coupling. And so that's something which is your ceiling comes down when you give up on the gauge invariance with higher spin particles, is kind of the physical content.
Yeah, maybe I just like add to it. We start, for example, people who do EFTs and study phenomenologically the Higgs sector and the LHC. We start from the standard model, which is a gauge invariant theory, and then you try to find new Higgs by assuming that you deviate or that you violate gauge invariance. For example, in the kappa framework, when you study kappa W or kappa Z, those are one in the standard model, but you essentially assume that they could deviate And of course, if you deviate from unity, then this means that the UV theory or the effective field theory that you're talking about essentially violates gauge invariance. I'm just wondering how sound this approach, or can I just say that kappa W must be to all orders, must be equal to 1 because I don't want to lose gauge invariance at all scales?
No, there's a physical choice there. Yeah, it does make sense, and so there will be ultraviolet theories for whom it will make sense to have at low energies kappa not 1, and those will be ones for which you've spontaneously broken the gauge invariance in a particular way, and the low energy limit, the way that very much like the example I had where when we look below the below the top quark mass, we looked at the effective theory of the W's and the Z's. In that effective theory, gauge invariance would have said that the W and the Z mass were tied to each other according to MW is MZ cosine theta. But what that really means is that linearly realized gauge invariance says that. If you non-linearly realize the gauge invariance, it's effectively it doesn't constrain the Lagrangian at all. And so it's effectively makes those two terms independent of one another. And so if you'd asked the same question about the W and Z masses, you might have said, well, if I require SU2 cross U1 invariance, they have to be coming from the Higgs kinetic term, and so they have to be related in that way, and so that's a consequence of gauge invariance. It doesn't mean that there's no physics I could have had at high energies which violates that prediction, and the top quark is an example of physics that violates that prediction. And so you're free to write in an effective theory things like kappa's not 1, that's not gauge invariant, but you have to be aware that the ceiling of that effective theory is much closer than you might have thought it was. It'll be something of order the gauge boson mass divided by the coupling. And so if you have to trust that theory past that, then you might be in trouble. But as long as you don't have to do that, then you could be okay.
I see. Thank you.
Yeah. So Ognivo, you can ask.
So my confusion may be very naive. So if I understood correctly, so the EFT technique is very useful if I have a theory at very high scale, new physics at very high scale, and I am in a very low regime. Then the EFT technique can help us to somehow model those effects in the low energy regime. Now the example you talk where like you are cutting off the Higgs and the top quark, now mass difference, but that's not that substantial, right? That Z and Higgs mass difference is not that much. So how well the EFT technique will work in that like small mass gap regime? Like whenever
in the case of, you're talking about the case of the Higgs in the top compared that specific example?
Yes. So because these are like same order of energy scale, right? We cannot say that that is very far.
Yeah. So the basic statement is that your observation is right that in all cases you're doing an expansion in powers of the masses, and so how effective that is, how powerful that is depends on what the ratio of the masses is.
Yes.
But it's often so but what's often true though is that that ratio doesn't have to be actually very. It depends on there's two roles that the ratio of masses could play. If the ratio of masses is actually the thing that's controlling your whole approximation, so for example in gravity, where you've got the ratio of scales is the thing that you're expanding in when you do the semi-classical approximation, then you're really tied to it. So if that ratio was a half, that would just mean that semi-classical gravity is a bad approximation and you should do something else. But in the case of the standard model, what's happening is that perturbation theory is being controlled by the dimensionless couplings. So you're using the effective theory not to control the approximation itself. You're using it to identify what's the big piece in the answer. And in that case, the m squared can be, although m over mw might only be, it's like a 2 or 3 or 2.5 or something. When you square it, you're getting a factor of 4. But that factor of 4 might make that twice as big as everything else. And so if you want the biggest contribution, and particularly if you want to float the value of the top mass in a fit and ask how sensitive are you to the different values as it varies, the parametric dependence is dominated by things like squares of the mass. And so it's something where, so the way people actually would, in practice, when they were doing that approximation, when they actually did it, they did not rely on the large m-top limit for doing the entire precise radiative corrections for the standard model. What they would do is they choose the value of the top quark and they do all the radiative corrections like that 1 loop or 2 loops or whatever, once and for all for that one value. But then when they wanted to float the top mass in a fit, what they do is they just follow the difference between the top mass and that fiducial value they used in their detailed calculation. And for that following of the mass, it was sufficient to track only the quadratic dependence or the logarithmic dependence on the masses.
Okay.
And that gave you that was much more efficient than repeating the entire complicated calculation for each value of the mass, which people also did. So you could compare the two ways of doing it. And so for this exercise, which is tracking the mass dependence in a fit, it was much more efficient to track just the quadratic piece, and then that was accurate enough because you weren't relying on it to control all of your loop calculations.
Thanks.
Good questions.
Yeah. Any other questions? I don't see any other hand. Okay. Okay, so if not, then perhaps we can thank Professor Burgess for this excellent talk.
Thank you very much for hanging in there right to the end. It's an hour and a half is always a long time for the audience, I think, not for the speaker.
Okay.
So hello, Shubhendu.
Yeah.
So we just hello, Professor Burgess. We just want to thank you on behalf of the organizers for this wonderful talk. Hopefully, in the future, you can visit us.
Yes, very much like to. Thank you for the invitation again. I very appreciate it very much. Good luck with the rest of the meeting.
Okay. So we will start again at 4.
Yeah. Okay. Yeah, we'll come back at 4. Yeah.
Bye-bye.
Bye, Cliff. See you.